Okay, so first I want to thank you for having our team to present our results. And my name is Bing Yao. And my teammate is Jiaqi Guo, and we are advised by Professor Wiswana Nagarajan. Okay, so I will pause in each session, so if you have any questions, feel free to ask. Okay, so I want to first start with introducing the features of this problem. So first, the graph is non-complete. So we will first calculate the shortest distance for all pairs of nodes using Digester's algorithm. And second, the big questions, the big part of this problem is to decide the number and locations of the depots. So we hope to utilize the statistic informations when making our decisions. Also, when we formulate our routing algorithm, we found the time windows and reload property is very important when formulate our algorithms. And finally, we found that typically the daily demands is less than 100 orders. So we can develop some efficient algorithms to solve it fast. So, okay, I want to give you the picture of the data. So first, the fixed cost of a depot is higher in urban areas. So you can see that most of the depots with high cost was located in Philadelphia and Pittsburgh. And also, when we look at the demand distribution, it has a clear pattern. So when we want to estimate the total cost, we want to sample the days that reflect this kind of seasonality. And also, we explore some other quantity, like the average quantity of single order. So they are actually quite stable, around 10, whatever regarding location or time. And finally, we also want to figure out the demand distributions regarding the locations, but it doesn't seem to have any patterns. So the urban area doesn't have greater demand comparing to the rural area. So given this observation, we want to start the first part of our models. When we first design the number of depots automatically, we want to consider the trade-off between several parts of the cost. When one goes lower, the other parts may go higher. So first, we estimate the lower bound and upper bound of the optimal number of depots and gradually narrow down the gap between these two bounds. So firstly, we will just set the lower bound as 2 because one depot cannot satisfy all the customers given the time window constraint. And for the upper bound, we calculate the average daily demand, which is around 840, and divided by the capacity of the vehicle, 60, so it's around 14. Then we pick out some representative number between the lower bound and the upper bound, and calculate the estimated total cost. And then we gradually narrow down the gap until we find the optimal number of depots. So we want to first introduce our location model. We use k-median clustering. So this is the integer programming formulation we have. So here, d of ij is the distance between I and the j. And we also put weight wj reflects the demand at customer j. So basically, when a customer has greater demand, it has higher weight. And we also set up two variables, xij and y of I. So s of ij equals to 1 if customer j is served by the depot I, and y of I equals to 1 if we maintain a depot at location I. So basically, the objective function enforces the depots to locate near the high demand area to reduce the total cost. And the first constraint means each customer is served by exactly one depot. And the second constraint means location I can serve customer J only when there's a depot at there. And the total number of depots is bounded by the preset K. And after we running the clustering algorithm, this is the running time. So basically you can see that it can be completed within at most 6 to 7 minutes. So after obtaining the clustering result, what we do two things. The first is to estimate the number of vehicles. We pick up the day with greatest demand and running our routing algorithms to obtain the estimation on the number of our vehicles. And the second part is to sample 10 to 15 days in a year that reflects the seasonality. And we run the routing algorithms to estimate the total annual routing cost. And combine all the information we have, then we can decide which number we want to use. The problem also requires us to think about the objective function with cost of depots. So the previous one doesn't include that. So one easy adaptation is just to include the part of the depot cost in our median clustering model. And here we also have a parameter lambda because the objective function is the total cost, and this is not a total cost. So we will set a parameter lambda to adjust this. And the way, okay, so if no questions, I can continue. So now we move to the routing process. So after the model, part one of our models, the problem has decomposed into many single depot vehicle routing problem with time window. Now we can apply some, our first attempt is to utilize heuristic methods. So the first step is to generate initial solutions in which every customer is assigned with a separate route. So this is the illustration of the first, the initial solution after step one. And after in step two, we will first try to merge these routes under there are two types of merging. The first one is simple and naive. So suppose a customer I is located at the shortest route from depot and customer J, then we simply just eliminate the routes that contains by the longer route. So now customer I and J both served by only one vehicle. And the more general case is to consider the combined any two rounds using the clock ride savings heuristic. So the basic idea is that for each two rounds, we will select 2 points that are adjacent to the depot and try to merging these two rounds by creating an arc from I to J directly. Then we see whether whether the rounds, the routing costs decrease, and also whether all the constraints are satisfied. If both are satisfied, then we can consider merging these two rounds to reduce the number of vehicles. And we repeat this step until we could not find a better solution. Then we move on to our step 3, applying some exchange heuristics like Lambda Interchange to search for better solution in our neighborhood. So I will give a quick explanation for what is Lambda Interchange here. So here we have two numbers, Lambda 1 and Lambda 2, that we preset before running the model. And then Lambda 1 simply means the number of customers we move from one route to the other. So I will give an example here. So this is the initial solution we have. and we set lambda 1 equals to lambda 2 equals to 1, then we will move after one implementation, one dark node will move from the route 1 to the route 2, and while one white node will move from the route 2 to the node route 1. So this is just local search method we use to find a better solution in our neighborhood. And this is basically the second part of our model. So any questions so far? Okay, so seems good. So I would like to also spend a few more minutes to talk about a method that we think is simple and interesting. So so think about there's a definition for single trip and multi-trip route. So single trip basically means you can only depart from the depot and return it once, while multi-trip means you can reload in the middle of the routes. So routing solutions for cluster can be viewed as a combination of single trip or multi-trip routes that all customers with orders are covered while all constraints are satisfied. So it's natural to apply the column generation methods where a column corresponds to a single trip route or multi-trip route. And I want to briefly introduce how the algorithm works here. So first we have a master problem. Here, tau omega is the set of all the single trip route we generate, and tau is the index of the routes. And then we have a C of tau, which means the total cost of running route tau, and plus the vehicle cost. So this is the cost of the selecting route tau. We also set a variable z of tau that equals to 1 if we select tau as active. So the A is just the column we mentioned. It corresponds to a column. So A of I tau equals to 1 if route tau serves customer I. So this constraint basically means each customers need to be covered by at least one route. So, and when we consider the pricing problems, it will become some we need to solve this minimization problem. Here, P is the door variables, and A is the column we need to generate. And we think these problems can transform into a shortest path problem. So think about this. So first, you have two copies of depots, so both S and T. So you need to find a route starting from the depot and end with the depots. And we also define distance between I and J, that is as C of ij minus half of the summation of Pi plus Pj. So here, C of ij is the routing cost from I to J. P is the door variable. Now we want to find out the shortest path from S to T, and this is typically can be done with dynamic programming. But for even for medium-sized instance, for like 20 customers, the state space will be humongous. So further, we applied a new approach, heuristic approach, to solve it. So this is called a random coloring. And the idea is quite simple. So first think about that. What is the typical number that a single trip can serve? So the capacity of the vehicle is 60, and the average quantity of single order is 10. So we assume a single trip can serve 6 customers. So now we do randomly assign the 6 different colors to all the customers. So as you can see in the illustration. So instead of finding a shortest path from S to T that visits 6 customers, we only need to consider finding a shortest route from S to T that covers that visits 6 different colors exactly once. And under this formulation, the size of the state space can reduce significantly. And now we can apply some dynamic programming to solve this problem. and repeat several times at each iteration to explore better solutions. So this is the part 3 of our model. So any questions so far? Oh,
I have perhaps one question which relates to, I guess, part one, all the previous parts.
this part?
Yeah. Can you perhaps explain a little bit better how you take into account the time windows for each customers? The fact that each customer has a delivery time window, what is the impact on this on the different algorithms that you are developing? How they are taken into account?
You mean the impact of the time window on this part?
Yes, on the routine first. Yeah.
Okay. So the good thing is that the time window is identical for each customer, so which can simplify our model. So I think, so maybe I can go back to this part. So when we consider how to apply the clockwise savings heuristic, what we do is to first find the possible combination, merging that has the greatest savings. So which means after the merging, the cost is reduced greatly, has the most savings. And then we will first consider the one with greatest saving, and then we check whether after we merging these two rounds, whether all the time window for the all the time window, whether it's still satisfied by all the vehicles and the customers. And I don't think it will involve lots of work. So basically, there are only 3 constraints we need to satisfy, I think.
Okay, thank you.
Oh, yeah. Okay. So, okay, I will move on to the experiment results. So all the result is based on the optimization method I mentioned before. So first, you can see that this is the objective value compares to the versus the time we use. So you can see that the value can drop very quickly and gradually converge to the optimum. And this is an instance for 10 customers. So basically it can run within 10 to 12 seconds. This is the time we used for estimating the total cost, as we mentioned in part 1 of the model. So in our settings, here we only use 10 minutes, roughly 10 minutes for each number k. And because we assume the total cost is unimodal, so it first decrease and then increase. So as we use the methodology we introduced before, we gradually narrow down the gaps and finally find k equals to 15 as the optimum. And this is also the running time for each cluster. So for small instance, it basically can run within a few seconds, while for medium-sized instance, the running time will become very relatively long. And I want to talk about the first questions, is to compare the different objectives. So on the left side, we exclude the cost of the depot in our objective. So it turns out to have 15 depots. So because the function aims at reduce the routing cost, so the total cost is not important here. After we include the cost of depots, the model will be more careful. So it will try to reduce the size of the depots. So here's more details for these 2 objective functions. So as you can see, if we don't if we exclude the depot, depot. We may include depots with extraordinarily high cost. And as you can see, the building cost is reduced significantly, while the routing cost doesn't increase that much. So overall, I think it's better to include the depot cost in our objective functions. And also, when we look at the CO2 emissions, the output result with depot cost is indeed higher than the solution without depot cost. So I think decision makers should value. It depends on whether the decision maker values the environments or the cost of running the of scheduling all the routing and routing schedule. So this is the basic the results we had for these two types of function. And also we consider question 3, where we run our models under two different demand, 2018 and 2019. And the good thing is that the number of depots doesn't change that much. They remains the same. So we both select 10 depots, and the number of vehicles do have a little bit difference. So we've hypothesized, we guessed this is because the structure of the demand. So for maybe the demand is a little bit lower than 2018, or the demand is more centralized around the depots, so the number of vehicles can decrease. So for the last part, we also explore the relationship between the routing cost and the demand. So we randomly select 16 points for a cluster, and they will draw the graph and see the relationship. So we think here we can apply some regression methods to figure out the function between the routing cost and the demand. So now I want to jump to the conclusion here. So we both test several different approaches, like heuristic and optimization methods for the routing algorithm. And the experiments suggest that it's better to include the depot cost as objective, which helps to obtain more reasonable solutions for the depots. And our model is relatively robust under data sets 2018 and 2019. And finally, so I want to say that it's promising to combine different approach, optimization and heuristic approach, to obtain a better solution in a reasonable time frame, because they both have their own merits. And thank you so much for listening to my presentation. Yeah, that's all.